Hello, welcome to the Math 159 Gould Chapter 5 Section 3 video, which is about associations and categorical variables. So in the 5-2 videos, we talked about calculating probabilities, probability of an event, theoretically, probability of an event with an and, or probability of an event with an or. We're going to talk about a new sort of probability today called conditional probabilities. Okay, so conditional probabilities are different than like probability of A, just the probability of an event. It's also different than the probability of A or B, or the probability of A and B. But it sort of looks like when you're calculating a probability of an and or an or, in the sense that there are also two criteria, or two events. So let me explain what do I mean by this. So when you calculate the probability of, type the probability of A or B, you're dealing with two criteria. It has to be A or B. Same thing when you're doing the probability of A and B, right? You need this and this to happen. We're dealing with two criteria or events. A conditional probability also deals with two criteria or events. The difference, one of the main differences though, is that when you're dealing with or and, the criteria are evaluated at the same time. So we're asking, like, at this moment, are both A and B happening? Or at this moment, is A or B happening? Okay, so when we're talking about conditional probability, we write the symbol like this: A given that B. So this is read as A given that B. So what this means is how many people who satisfy event B also satisfy event A. So you can sort of think of this as a sequence of events. We're saying, hey, it's a given that B happened. Now, for how many of those did A happen? Okay, and so we would write this as the probability of A given that B. The probability of A given that B has occurred. So that's what I mean by it's a sequence of events. Like, we're saying, look, B happened. Whatever B is, done. Now we're wondering, in those cases, what's the chance that A happens? Okay, so let's do an example here with a table. So we're going to go back to our book, what's it called? The book data. And we're going to use the same event. We're going to say event A is that the book is a hardcover. Event B will be that the book is nonfiction. So what's A given that B? So it's given that the book is nonfiction. Given that the book is nonfiction, we want to see that the book is also a hardcover. So if we're doing the probability of A given that B, we want to know the probability that a book is a hardcover given that the book is nonfiction. Okay, so usually when we write this, we sort of write it, well, it goes like in the same order as this. So remember, A is that it's hardcover, but it's given that it is nonfiction. So when you think about this, you have to first constrict yourself only to how many books there are that are nonfiction. Oops. Okay, so when we calculate this, we're only considering the books that are nonfiction. So I'm going to change over to, oops, what's going on? It's not letting me change. Come on, switch. Boom, okay, cool. Okay, so let's make our table. We're going to go stat, tables, contingency, with data row variable is going to be hardcover, column variable is going to be nonfiction. Okay, so remember we are, what's the word I'm looking for here? Restricting ourselves to books that are nonfiction, because that's our given. So the columns are nonfiction. So in total, the columns are nonfiction. Oops, why is it not letting me select it? 1 means that it is nonfiction. So how many books in total are there that are nonfiction? 22. So that's going to be my denominator. I'm going to put 22 here because there are 22 books which are non-fiction, and that is my given. Now the question is, hey, of the books that are non-fiction, how many of those are a hardcover? So we can go back and we look, and hardcover is this row right here. So remember, we were looking at the column with the 1. So of those 22 books, 3 of them are hardcover, and that will be our numerator. So the answer to this is 3 out of 22, which, if you calculate that, I would like to calculate that right here. 3 out of 22 is 0.1364, which is 13.7%. So from that data we had, hey, what's the chance that if you choose a nonfiction book that it's going to be a hardcover? So this is the probability that if you choose a non-fiction book that it is a hard cover. So notice we're restricting ourselves to non-fiction books, and then we want to know something about that. Okay. So let me give you an example now where we use a formula to do this. So the formula to do this, the probability of A given that B, is written as the probability of A and B divided by the probability of B. Let me write the little line. So notice the given determines the denominator probability. And this makes sense because we're saying, like, look, it's a given that B has happened. B is true, which is why you're dividing by the probability of B. Now, of those cases where B is true, I want to know the probability that both A and B are true. Okay? So let's do an example of this. Let's do the example with, what was it called? Our die. So A is going to be that the sum is greater than or equal to 10, and event B is going to be that the first die is even. Okay. So let's start off by writing out all the possibilities for B. The first die has to be even, which means I can roll a 2 and a 1, a 2 and a 2, a 2 and a 3, a 2 and a 4, a 2 and a 5, a 2 and a 6. The next even number is 4, so I can roll a 4 and a 1, a 4 and a 2, a 4 and a 3, a 4 and a 4, a 4 and a 5, a 4 and a 6. The next number that the first die can be even with is 6, so 6 and a 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. Okay, now let's work through the A events. The A events are the sum is greater than 10. So can I roll a 1 and get a sum greater than 6? No, 10? No, because that'd be 1 plus 6 would be 7. Can I roll a 2? 2 and 6 would be 8. Can I roll a 3? 3 and 6 would be 9. No. Can I roll a 4? Yes, I can roll a 4 and a 6 and I get 10. I could roll a 5 and a 6, a 5 and a 5. I can roll a 6 and a 6, a 6 and a 5, and a 6 and a 4. Okay, cool. So, according to this, if I want to calculate the probability, I need to put the probability of B on the bottom. Well, what is the probability of B? Well, B has 1, 2, 3, 1, 2, 3, 4, 5, 6. 3 times 6, there are 18 ways to satisfy event B, my given. And how many different total rolls were there? 36. So I get 18 out of 36 as my bottom number. Now, what's the probability of A and B? Well, we need to look to see the overlap between the two of them. 4 and 6 are shared. 5, 5, and 5, 6 do not show up in A. 6, 4, 6, 5, and 6, 6 are shared. So in total, there are 1, 2, 3, 4 shared events. So you get 4 out of 36. So if you calculate this, this becomes 4 out of 36 times the reciprocal. So you get 36 over 18. The 36's cancel. You are left with 4 over 18, which is 2 over 9. And 2 divided by 9 is 0.222. That is 22.2%. There's a 22.2% chance that if you roll and your first die is even, because that's the given, that your sum will be greater than 10. So let's write this down. There is a 22.2% chance or probability that if your first die is even, that the sum of the two die is greater than or equal to 10. Okay, so if you have an even die, boom, that's the if you think of it this way, let's say you're rolling 2 die and you roll your first die and you're like, oh shoot, my first die is even. Now you know that you have a 22.2% chance that when you roll that second die, that your sum will be greater than 10. Okay. So you need to be careful about conditional events. A lot of people make the mistake and think that the probability of A given B is the same as the probability of B given A. That's not true. These in general are not equal to each other. So don't make that mistake. And we're going to talk about something related to this. There's something called independent and dependent events. Alright, so we're going to talk about independent and dependent events. So what are independent events? Independent events have no effect on each other. And let me explain what I mean by that. So let's look at the probability of A given that B. So we're saying, look, B has happened. If B has no effect on A, then this will be the same thing as the probability of A. What we're saying is that if B happens, then it has not changed the probability that A happens. So in other words, B occurring doesn't change the probability of A occurring. Okay, I can't spell occurring properly. Okay. If they are dependent, then this will be different. The probability of A given that B will not be equal to the probability of A. So let's do an example here. Let's say that A is a baby will develop food allergies. Event B will be baby is premature. Or baby has food allergies. There we go. And event B is that a baby is born prematurely. So I looked into this, and I don't have the links anymore, but there's actual research backing this up. The probability that a baby ends up getting food allergies is about 7.6%. And the probability that a baby has food allergies, given that it was born premature, is about 4.23%. Now, they aren't exactly the same, but they're close enough to each other that they are the same, and we're going to discuss this in the future. But, well, how close do they need to be exactly the same? Usually not really, they just need to be close enough. So we would actually say that, and there's a lot of research that these, and sometimes, I guess I should say this, when they've done studies, the numbers are never going to be exactly the same each time. So in statistics, there are methods to say like, 7.6% is close enough to 4.23%. And we'll actually learn how to do that in a later section. So it looks like being born prematurely has no effect on you having food allergies later in life. In other words, the events are independent. Being born prematurely has no effect on whether you get food allergies. So let's do another example of this. And this one we'll do with a card deck. So let's say that A is you draw a diamond. Can't spell. B will be that you draw a red card. So let's write down some probabilities here. The probability that you draw a diamond is 13 out of 52. Why is that? Well, because each suit has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and Ace. And if you count that, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, so this should be 14. Wait. Oh, sorry, there are no ones. That is 13. Because if you count these, you'll see that there are 13 different cards for each suit, because each suit has a card with that face. So drawing a diamond is, probability of that is 13 out of 52. Okay, so now let's calculate, what's the probability of drawing a diamond, given that you have already drawn a red card. Okay, so we could use the formula, or we could sort of think this through. How many red cards are there? Well, there are 52 cards, and half of them are red. So you get 26 as the numerator. Now, of those 26 cards, how many are diamond? Well, red cards are the diamonds and the hearts. There are 13 diamonds and there are 13 hearts. So of those 26 red cards, 13 of them are diamonds. 13 over 26 is 1/2, which is 50%. The probability of drawing a diamond is 13 out of 52, which, if you reduce that, that's going to be 1 out of 4, which is 25%. Notice that these are not the same. The probability of A, in this case, is not equal to the probability of A given B. In other words, the events are dependent. If you draw a red card, then the chance of it being a diamond is increased. So if you just draw a card, the chance that it's a diamond is 25%. But if, let's say, someone draws a card for you, looks at it, and tells you that it is a red card, you now know that you have a 50% chance of it being a diamond. Okay, it increases your chances of that happening. Okay. Last example, we're going to talk about a formula. So remember I talked earlier about, you can think of this as a sequence of events. So like for this one, if someone draws a card for you and it's a red card, Then what's the chance that it's a diamond? You can think of like that's one event and then the next event. So let's talk about this as a formula for a sequence of events. So there's a formula that says the probability of A and B is equal to the probability of A times the probability of B given A. Okay. And usually the way we actually look at this formula is this way, as the probability of B given A is equal to the probability of A and B divided by the probability of A. All I did was, oh no. One second. There we go, my keyboard got stuck. So the probability of B given A is the probability of A and B divided by the probability of A. So notice the second one ends up on the bottom here. Okay. And more importantly, so this always works, this formula. We've actually already talked about it. But if the events are independent, then the probability of A and B is just, or is equal to, the probability of A times the probability of B. I can't type. So instead of this more complicated formula, if the events are independent, you can just multiply their individual probabilities. So let's do an example. Let's say that A is event that the first child born is a boy. Event B is that the second child born is a boy. So this is a sequence of events because we're talking about the first child is this and then the second child is this. Like one obviously occurs after another. There is a lot of research which tells us that the gender of one child is independent of the gender of another child. And now we need to know, hey, what's the probability that a boy is born? So what is the chance that a boy is born? Interestingly enough, the chance that a boy is born is about 51%, and the chance that a girl is born is about 49%. They theorize that this has to do with the fact that boys are more likely to be aggressive and take risks, so they're more likely to die, so you have to have more boys born because to get a 50-50 balance. And actually boys are more likely to die during childbirth than girls, so it evens out. It ends up being 50-50 over time, but you need more boys to be born to make that happen. Okay, so what is the probability of A and B? Well, they're independent, so it's just the probability of A times the probability of B. And the probability that a boy is born is 0.51. And then the probability that a boy is born is 0.51. And 0.51 times 0.51 equals 0.2601. There is a 26% chance that your first child is a boy, and then your second child is also a boy. Let's contrast this with saying, hey, what's the chance that your first child born is a girl, and your second child born is a girl? Again, these are independent. So we do the probability of A and B. That's the probability of A times the probability of B. Chance that a girl is born is 0.49. Chance that a girl is born is 0.49. Which ends up being 24.01. The chance of having back-to-back girls is 24%, slightly lower than the chance of having back-to-back boys, which is 26%. Thank you for watching the video. This is the end.